Good morning, ladies and gentlemen. My name is Dario Polli and I'm from Politecnico di Milano in Italy. First of all, I would like to thank the organizers for inviting me here to present this work entitled Broadband, Coherent Raman Spectroscopy for Nonlinear Label-Free Microscopy. I would like to thank all the people involved in this research. Without them, almost nothing of what you will see would be possible. Optical microscopy represents an extremely powerful investigation tool for life sciences, thanks to its ability of visualizing morphological details in cells and tissues on the sub-micrometer scale. Fluorescence microscopy, in particular, can use exogenous markers such as fluorescent dyes or semiconductor quantum dots with a palette of colors. Here you see, for example, the absorption and emission spectra of 6 chromophores that you can use. Or you can use endogenous markers such as fluorescent proteins. Here you see, for example, the famous green fluorescent protein. You can induce the expression of the gene related to GFP throughout a given organism or in a selected organ or in cells of interest. There are also other variants with different colors such as blue, cyan or yellow color. All these markers offer superb sensitivity down to the single molecule limit. However, there is a problem, because sometimes adding such fluorophores cannot be implemented in some cells or tissues. Sometimes they give a strong perturbation in the investigated systems because they are too big. Or they can induce phototoxicity, especially when you use blue light to excite the sample. Or they can create reactive oxygen species that can damage the sample. So the aim of this research is to find an intrinsic and label-free imaging method. The solution to this problem comes from Raman spectroscopy. In fact, every component of a biological specimen, it could be a cell or a tissue, is characterized by a vibrational spectrum, such as this one, that reflects its molecular structure and provides an endogenous and chemically specific signature for its identification. Now, each peak depends on the weight of the mass and on the strength of the atomic bond, the spring, such as in this case. The vibrational spectrum, therefore, can be used as a kind of fingerprint, providing a chemical signature to uniquely identify tissue states. Furthermore, this technique is non-invasive, as it does not require any staining or labeling of the molecules. Now, in spontaneous Raman, a continuous wave laser excites the sample, and 1 every 10 to the 7 photons is inelastically scattered. It's called Stokes, and the frequency difference between the pump and the Stokes will represent the frequency omega of interest. In this example, you can see, using spontaneous Raman, a fiber is inserted into this needle, which enters a human brain. Then, at the end of the fiber, infrared light excites the tissue. Now, inelastically scattered photons will be collected through this ring of fibers with some filters to reject the fundamental light, and then the Stokes will reach the spectrometer. And by measuring these spectra, you can distinguish different tissue states, for example, normal from tumor state, with very high specificity and sensitivity. Now, specificity, it's also called true positive rate, measures the proportion of actual positives which are correctly identified as such. You can see, for example, in spontaneous Raman, this is more than 90%. With respect to the gold standard clinical practice, which is staining the tissue with hematoxylin and eosin, which colors the cells and the cytoplasm with these pink and blue colors. In this example, H&E staining provides a sensitivity lower than 70%. And also the specificity provided by Raman spectroscopy is much higher than the standard practice. Now, specificity is also called the true negative rate, measures the proportion of negatives which are correctly identified as such. And as you can see, this is true for many organs, not only in the brain, but also in the esophagus, in the breast, colon, and bladder. Now, the only problem of spontaneous Raman is the very low cross-section, which provides very low speed. It typically takes around, say, 1 second for measuring a high-quality spectrum, so that to acquire a high-definition image would require almost the entire day. As a result, this has prevented its mainstream clinical use. To summarize, spontaneous Raman provides a wealth of information, but at very low speed. The solution to increase the speed is coherent Raman. Now, in this cartoon you see spontaneous Raman on the left, which employs a continuous wave laser, it's called pump, this is the beam waist at its focus, to detect the random thermal vibration of the molecules at a certain frequency, say omega. Now, on the right, in coherent Raman, the coherent superposition of two narrowband lasers, they are called pump at omega p and Stokes at omega s, makes the molecules to vibrate in phase so that the signal is enhanced by many orders of magnitude, making high-speed three-dimensional imaging possible. Now, if another molecule is present vibrating at a different frequency, say omega prime, using spontaneous Raman it is also possible to detect it. In coherent Raman, this is in general not possible because the second molecule, the second molecular mode, will not fulfill this resonance condition. So the problem is how to go from single color coherent Raman to multiple color coherent Raman, which is typically called multiplex or broadband coherent Raman. Now, coherent Raman is a third-order nonlinear optical process. You typically need, as a laser source, two narrowband picosecond synchronized pulses, as shown here. In stimulated Raman scattering, SRS, the vibration at a frequency, say capital omega, is detected either monitoring the annihilation of a pump photon, also called stimulated Raman loss, or the emission of a Stokes photon, called stimulated Raman gain. These are very small signals, typically a part in 10 to the 5 or 10 to the 4, so that you typically use modulation transfer techniques in which one beam is modulated in amplitude using an acousto-optical or electro-optical modulator, and the small modulation transfer on the other beam is detected with lock-in amplifiers. To summarize, spontaneous Raman displays a very high information content but with very low imaging speed, while coherent Raman provides very high imaging speed but in its standard implementation delivers limited information on the sample, being capable of detecting just one or a few vibrational modes. The aim of my research is to develop a fast and broadband coherent Raman scattering microscopy setup with the final goal to image a tissue and in each and every position of the sample to detect the full Raman spectrum and in this way distinguish, for example, healthy tissue from tumors. The problem is how to move from single color to broadband multiplex multicolor stimulated Raman scattering technique. I will present you two key ingredients that are required in order to achieve this task. The first one is to use the so-called balance detection to increase the signal-to-noise ratio, and the second is to use a broadband approach to SRS. We have proposed several methods, and in particular we'll present the most recent one based on a multi-channel lock-in amplifier. So let's first start with the balance detection. What is balance detection? Well, typically you want to use fiber lasers for coherent Raman microscopy because they are small, they are cheap, they are turnkey, and very easy to operate. Unfortunately, sometimes fiber lasers have high relative intensity noise fluctuations, and then you need to compensate for them using a balance detection. So balance detection typically is performed in this way. You split some of the stokes, in this case light, before the sample, and you use a second photodiode. Now in this second photodiode you will only measure the noise of the laser fluctuations, while in the other one you will both measure the signal coming from the sample and the noise of the laser. Now, by subtraction of these two signals, you should be able in principle to remove the laser noise and to only detect the signal from the sample. Now, unfortunately, this is not always the case, because when you scan the sample, either by moving the sample or by moving the beam with respect to the sample will have a variable transmission as a function of x and y, so that your detector on the right hand side will vary the transmission, and so you will unbalance the system, and so this balancing, this subtraction will not be anymore performed in the right way. As you see here, the Stokes typically has a 1/f noise performance, and then at a certain point you reach typically a kind of plateau, and you have to detect this tiny signal, because SRS detects this SRL or SRG small variation on top of the Stokes. Now, if you subtract the reference which has the same noise performances, you will end up into a better signal to noise ratio, because your signal now is pure, and you typically reach the shot noise, or actually 3 dB above the shot noise, because of course the shot noise will be happening independently over the two balanced photodiodes. Now, how can you solve this issue of having an automatic balancing even if the sample has a variable transmission? Well, we invented this technique which is called inline balance detection, IBD. In this case, there are two steps. First, we generate two replicas. Here we enter at 45 degrees a birefringent crystal. If the phase axis is, as you see here, oriented horizontally, then your 50% of the light, which is horizontally polarized, will travel faster, and so it will come to the sample as a first pulse. And then after a certain delay tau, you will have the vertical polarized light, which is in our case the Stokes. Now you sum up the pump together with the Stokes, so they will come with the same polarization and at the same time and on the same place on the sample. But before that, you have the reference. The delay between the two should be something about 10 picoseconds, so that all the vibrational coherence is totally lost before the arrival of the pump and the Stokes. And then having also the 90 degrees polarization will also help to reduce any possible SRS on top of the reference. So the reference goes through without any signal, and then after the sample you have either a polarizing beam splitter or a Wollaston prism. You separate the two polarizations, and you will have on one photodiode the Stokes plus the signal, and on the other just the reference. Then you do a simple subtraction with a standard commercial balanced photodiode, and this signal will enter a single channel locking amplifier as usual. So that in any microscope setup, if you want to implement the IBD, you just need to add a birefringent crystal and the half-wave plate, if you wish, before the sample, and then after the sample you replace your single photodiode with two photodiodes, and you have a polarizing beam splitter or a Wollaston plate. Now, this works very nicely. In particular, Vikas Kumar and Francesco Crisafi performed these experiments a few years ago. And as you see, in the unbalanced case, we have a much lower sensitivity than with the balanced case here, the black squares. We reach an improvement of signal-to-noise ratio of the order of 30 dB. Then these are a few exemplary images. On the left, we are imaging a cell from this cancer line of liver cells, HEPA-RG. And on the right-hand side is the same image at the same measurement time using the IBD technology. As you see, the results are much better in terms of signal-to-noise ratio. This is a second example using a different cell line. This is HU-H7. On the left, again, the unbalanced, and on the right, the balanced case. And then you can also do three-dimensional imaging, changing the focus at the sample, and you can reconstruct these very nice movies in which you see, in particular, these were lipid droplets resonant at this Raman shift. The second ingredient is broadband SRS. So we coupled this inline balance detection with a broadband approach. How can you do broadband SRS? Well, the first idea is to scan the color of one of the two pulses. For example, you can scan the Stokes with respect to the pump, so their frequency difference, capital omega, will change, and so you can measure with the series approach the entire spectrum of interest. But there is a better way to measure simultaneously in parallel all the vibrational features of your sample. Well, you just need to replace one of the two pulses, could be either the pump or the Stokes, with a broadband femtosecond pulse. In this way, you monitor at the same time, in parallel, simultaneously, all these vibrations. So the result will be that you will have these tiny peaks popping up on top of the spectrum. Now, the problem is how to measure these tiny variations, because you might recall, as I said before, that these signals are very small. Here they are just for sake of clarity enlarged by many orders of magnitude, but in reality you have to detect tiny changes of the order of 4 or 5 orders of magnitude lower than the spectrum at very high frequency, because typically you use 80 megahertz or 40 megahertz repetition rate lasers, and there are no spectrometers capable of measuring millions of spectra per second with such a high signal to noise ratio. So you have to find a new way. Proposed 4 different techniques. I will just present the first one here for sake of time, which is the multi-channel lock-in amplifier approach. But we have also proposed other techniques. The second is using a photonic time stretching, in which you send the pulse after the sample through a very long optical fiber. In this way, it is chirped and stretched up to nanosecond durations, and then you can use a very fast photodiode and very fast analog to digital card to sample the pulse and measure the spectrum in time. The second approach is using a wavelength scanning method, in which after the sample you go into a grating and then you scan the color on the photodiode by moving a galvanometric mirror at very high speed. And the third is to use the time domain approach, the Fourier transform domain approach, which is similar to the FTIR that you typically use in the infrared or mid-infrared. Okay, so let's move to the first of these 4 techniques, which is the multi-channel lock-in amplifier. So typically in broadband SRS, what you do is the following. You have the 2 pulses, the pump and the Stokes. One is narrowband and one is broadband. In this case, the Stokes is broadband and the pump is narrowband. Then you modulate the pump using an acousto-optic modulator or an electro-optic modulator. Then you couple them together using a dichroic mirror, and the 2 pulses enter your microscope, and then you are typically working in transmission geometry. You filter out the pump, and the Stokes is now modulated, and then you enter a grating or a prism spectrometer. You disperse the various colors, and then you detect them using a photodiode array. Now, when you switch on and off the pump, you will see that the spectrum changes. Now, if you connect a multi-channel lock-in amplifier into this multi-channel photodiode array, you will then demodulate the signal and you will select these modes, and so you will get a pure Raman spectrum, very similar to the one that you can detect using spontaneous Raman. This is the experimental setup that we have been using. This is, as I said, mainly a work by Alejandro de la Cadena. We start from a laser. This is a commercial laser ytterbium oscillator at 80 megahertz repetition rate, delivering pulses at around 1 micron. Part of these pulses are then spectrally shrinked to a narrow line using an ethalon to select a narrow portion, and then they are modulated using an acousto-optic modulator. Then you enter a delay line in order to synchronize the 2 pulses, and then they are coupled to the pump pulses using a dichroic mirror. Then on the other hand, part of the laser is sent to a home-built optical parametric oscillator, which we built in 2017. Then we have a prism compressor to pre-compensate, to pre-chirp with a negative chirp the pulses in order to compensate for the optics, mainly the objective, which is very dispersive. And then we enter the half-wave plate and the YVO4 birefringent crystal, which is, as I said, useful for balance detection. And then we enter into a home-built upright microscope. The light goes down into the sample, then is collected in transmission geometry with another microscope objective. And then we enter into a grating. The grating disperses the light. And then we select the signal and the reference beams using a polarizing beam splitter, as I said before. And the two arms are then focused using cylindrical lenses into two photodiode arrays, 32 channels, vertical array here for the signal and the other one for the reference. This is our first prototype of the board. This was only using 4-channel lock-in amplifier. So you see here on the bottom the two photodiode arrays for the signal on the left and for the reference on the right. Then here in the center you will see the integrated circuit. This chip has 4 balanced channels which work at high repetition rate from 1 to 10 megahertz modulation frequency with very high sensitivity. You can also select the gain with variable levels in order to be able to work both at high or low illumination levels. Then you have all the electronics. For example, you have on board the analog to digital card conversion with a high frame rate in order to transfer only the demodulated signals onto the computer. And this is a close-up of the chip. It's just 6.6 millimeters squared, and it was designed using the 0.35 microns CMOS technology. This is the new version. This is equipped with 8 boards, each one having this chip of 4 channels. So in total we have 32 channels, and is just 20 centimeters in size. This is just a brief explanation of the working principle. You have the 2 photodiodes for the signal and for the reference. Then you have a first preamplifier, and then you subtract the 2 signals. Then you enter into a mixer. This is a real demodulation unit which is synchronized with the clock of the modulation frequency. And then you enter a filtering unit, and then up to here everything is analog, and then you digitize. You go from the analog to digital conversion card, and then you have an FPGA to compute all the calculations, and then you send the data to the computer. These are some results. We were imaging 4 different elements. In yellow there is oil, in blue DMSO, a solvent. Then there are PMMA and polystyrene beads. And for all these signals, you have 32 channels, so we built 32 images in parallel. These are just 4 of these 32 images. One is here resonant with the oil at this frequency, so you see that oil was filling these gaps. Then on top of the DMSO, you have a DMSO signal, especially in this corner. And then you have on the peak of the PMMA signal, you have these PMMA beads, which are small ones. And then you have large polystyrene spheres here in this other region. Then if you take this 32-channel hyperspectral image and you do some computations using, for example, the multivariate curve resolution analysis, you can in fact distinguish the 4 components with these 4 spectra and with these concentrations. So you see in yellow there is the oil, in blue at this corner here you have the DMSO, and then you have the PMMA and the polystyrene beads. This is a picture of our home-built upright microscope. The light is sent from the top to the bottom. You can see here also a close-up of the upper part and of the lower part. And these are some recent results. We have been studying a tumor model, a mouse fibrosarcoma. So in particular, we selected this tissue. You can see with the H&E staining that the tissue is divided into a cancer region here, and there is some healthy muscle at this corner, and then there are some interfacial regions in between. So let's zoom a bit inside region. You see here there is the cancer on the top, the healthy muscle on the bottom, and there is this interface. Now let's zoom again even more. You see this slice. This is the adjacent H&E slice, and then is the following. We imaged using SRS. using label-free stimulated Raman scattering. These are just 3 of the 32 images that are collected in parallel at 3 different vibrational modes in the CH stretching region. Then if you take all of them and you compute again the multivariate curve resolution analysis, you can do the following. You see, these are the 3 bands that I was plotting here. This is the average spectrum on the cancer region, which is this one on the top, while this one is the average spectrum of the healthy region here on the bottom. If you do the multivariate curve resolution analysis, you can distinguish indeed the 2 species in red for the cancer and in green for the healthy tissue. And then by plotting the concentration of these 2 species, you can see indeed that we can, using a coherent Raman spectroscopy and microscopy, you can distinguish the cancer from the healthy connective tissue. Thank you very much for your attention.